Hello students, welcome to online lesson 1. Just before you went home, we are dealing with the topic of electrochemistry. Today we're going to move on with one lesson that is going to tell us a little bit more from where we left. We'd already talked about oxidation numbers, and also we talked about how to calculate the oxidation numbers, what is electrochemistry, and all the other introductory stuff. For today, we're going to look at the standard hydrogen half cell. The standard hydrogen half cell looks something like this here. Now this is how you draw it. Now the standard hydrogen half cell is usually chosen as the reference electrode and is assigned the voltage of 0.00 volts. Now these are the components of the standard hydrogen half cell. Here we have a connecting wire. This is a beacon, and from this end we pump in hydrogen gas at a temperature of 25 degrees Celsius and pressure of 1 atmosphere. Now when the hydrogen is pumped here, it meets up with the electrolyte, which is a solution containing 1 molar hydrogen ions. And the surface on which the hydrogen and the hydrogen ion system gets into contact is a platinized platinum metal. During the process of operating the hydrogen half cell, bubbles of hydrogen gas are usually seen. Now, being the reference electrode, as I said earlier, it is assigned an electrode potential of 0.00 volts, meaning that all the other half cells are measured against it. The standard conditions for measuring the standard electrode potential are 25 degrees Celsius, 1 atmosphere, and all solutions must be 1 molar. The platinized platinum is used as the electrode for the hydrogen half cell, and it is always used when the electrode does not include a metal, for instance in this case hydrogen. Since it provides a surface on which hydrogen and the hydrogen ion system gets into contact, then the equation that takes place when hydrogen is ionized here is that hydrogen gas Now here, this equation shows us that hydrogen gas undergoes dissociation in order to make hydrogen ions. In that case, hydrogen loses 2 electrons, so it undergoes a process of oxidation. Also, the platinized platinum acts as an external electrical conductor to the circuit. Apart from that, it acts as an inert metal to connect the hydrogen and the hydrogen ion system. Now the hydrogen electrode, as I said, consists of an inert metal like platinum, which is platinized platinum, in contact with the 1 molar solution, and hydrogen gas is pumped through as apparatus that looks like this. The standard hydrogen half cell is represented as follows. The standard electrode potential for this half cell, as we said earlier, is 0.00 volts, which means that the half cell equation can be represented like this. Electrode potential, which is represented by E theta. E theta is showing us that this is the electrode potential under standard conditions, is equal to 0.00 volts. The standard electrode potential of any element versus its element ions half cell is taken as the difference between the potential of that element with that of the hydrogen half cell. When the hydrogen half cell and the zinc half cell are connected, the diagram representing the electrochemical cell looks like this. Now in this diagram, you'll notice that the hydrogen is on the right hand side. This is because between hydrogen and zinc has a higher tendency of losing electrons, and therefore it is a stronger reducing agent and is always placed on the left hand side. So as a rule of thumb, the element or the half cell containing the element that has the stronger reducing agent is always placed on the left hand side and the other one on the right hand side. Always remember to indicate the salt bridge and 1 molar solutions of each of the solutions for each of the half cells. Now once we carry out the experiment of connecting the hydrogen half cell to the other elements or other half cells, such as the one for fluorine, chlorine, bromine, and so on, you'll notice that the voltage that is indicated on the voltmeter right here is different from each of them. This is because it is done in reference to that one of hydrogen. Now, as you look at this list here, it is the electrochemical series that shows us the hydrogen half cell is the reference electrode with a voltage of 0.00. All the other elements are measured against the hydrogen half cell, and the voltage values that are obtained from the experiment are given here. If an element is a stronger reducing agent than hydrogen, then the electrode potential value will be a negative, like you see from lead all the way down to lithium. On the other hand, if an element is a weaker reducing agent than hydrogen, then the electrode potential is going to be a positive sign. In this case, you can see from copper all the way to fluorine. Now we want to look at the uses of standard electrode potentials. Number one, standard electrode potentials are used in comparing the oxidizing and reducing powers of substances. Now, just like we had said before, you can see that the different elements or substances here have different oxidizing and reducing powers. Fluorine is the strongest oxidizing agent, while at the same time is the weakest reducing agent. On the other hand, lithium is the weakest oxidizing agent and the strongest reducing agent. Use number two. Standard electrode potentials are also used in determining the EMF of a cell. Now, when we combine two cells, like the one we did for the standard electrode potentials, the zinc and hydrogen cell, then the overall cell has an electrode potential, or let's say an electromotive force, the EMF. The electromotive force of the overall cell can be calculated using the standard electrode potentials. I will be showing you this in a short while. Electrode potentials can be used to predict whether or not a reaction is going to take place. Now, in this case, we're going to use an example so that you can work it out and see how it can be used. Now, the question for the example is, the reduction potential of the copper zinc half cells are given here. Now, in order to calculate the EMF, the first thing we need to know is to write the ionic equation for the cell made by combining the two half cells. Now, in this case, before we start, we need to understand that the half cell made by combining the electrochemical cell made by combining the two half cells is going to have copper half cell on one side and zinc half cell on the other. But to determine which one is going to be on the left hand side and which one is going to be on the right hand side, then we have to look at the electrode potentials. Now, since zinc is more negative than copper, then the electrode potential of zinc is more negative than that of copper. Then zinc is a stronger reducing agent, meaning it has a higher tendency of losing electrons. Therefore, it will definitely be placed on the left hand side. And that would mean that the half cell equation for the zinc half cell is going to be the opposite. Since zinc is going to lose electrons, in this equation we can see that zinc ions are gaining electrons. But since zinc has a higher tendency of losing electrons, then the opposite process is more likely to happen. And therefore, we have zinc losing electrons to form zinc ions. And since we reversed this equation, then our E theta value for this equation that we have just written here is going to be positive 0.76. So in essence, we reverse the equation of the stronger reducing agent and revise the sign of the electrode potential. The one for copper remains the same. Electrode potential remains the same as well. Now, the overall ionic equation for this reaction is going to be given by the addition of these two. So on the reactant side, we have zinc and copper 2 ions. Since the two electrons are appearing on this side and 2 on the product side, they will cross each other out and we will not write them in the ionic equation. Now, for the second part of the question is to calculate the EMF of this cell. Now, in this case, it's going to be very simple. Since we have already reversed this, we're just like we added the equations, we also add the electrode potentials that we've written in here. So it's going to be positive 0.76 volts plus positive 0.34 volts, giving us positive 1.1 volts. And remember the sign. It is very important to have your sign, because if you lose the sign, it's going to be penalized. The next is going to be write the cell notation. Now the cell notation is going to be, since zinc is the one that is going to be oxidized, therefore we start with cell for zinc. Then we write the salt bridge, which is represented by a double line. And then finally we write the copper half cell, but this time we reverse this because copper undergoes reduction, so we begin from copper ions to copper metal. The E cell value, or the electromotive force, is therefore going to be given as positive 1.1 volts. Finally, it is to draw a diagram to represent the electrochemical cell. So this one I'll proceed as follows. Now, when drawing a diagram to represent the electrochemical cell of the zinc copper cell half cells, then there are key things that you must take note. You must show the voltmeter, you must show the copper electrode, which is the copper metal, then the solution, which is 1 molar, and then you must indicate the salt bridge, then you must indicate also the anode side, which is the zinc metal, and the solution. Another question that is commonly asked is showing the flow of electrons, and in this case the electrons will flow in that direction. Now it is important to note that the zinc metal is the negatively charged electrode, and therefore it is the anode. And on the other side, the copper electrode is the positively charged electrode, and therefore it is the cathode. And now it is time to test your understanding. Now, attempt the following question. The reduction potential of the iron and zinc half cells are given here. So the first question, we're just going to follow the same fashion as what we did, is to write the ionic equation for the cell made by combining the two half cells. And then secondly, it is to calculate the EMF. The cell notation for the cell. And finally, is to draw a diagram electrochemical cell. Now, give that an attempt, and apart from that, I'd like to give you some extra work. Go to your KLB book 4. The extra work is in KLB book 4. That is on page 136. 137, the revision exercise number 9 and 10. Now, once you do that, next lesson, we're going to look at the answers to this question and plus this extra work. So be sure to work on that and see you in the next lesson.